no indication to the hardware rate mirroring. If you read the block from one location and the read succeeds physically, but the block is corrupted, Oracle will try to reread the block, but there's no guarantee that RAID array will catch it from a new location, from another location. What it means that using ASM, you can recover not just from the media failures when the read actually fails, you can recover from like block corruption from the back checksum, or block the sort of block SCN scenario. When read of a primary extent fails, remember that Oracle always tries to read primary extent. If read of a primary extent fails, then Oracle will try to read from the secondary, and if the block from the secondary extent comes good, ASM will try to fix the block, to fix the extent which is corrupted, right? And that's called remapping. So it's not always happening. Sometimes, if you need to write the extent, you always need to log it. So depending on the context where the failure happened, Oracle process not always can sort of log this extent, and do the remapping. But most of the time it will happen. The way fix is working is that Oracle will try to write to the same location first, because often the disk themselves or the storage array behind have a technology to automatically write a block to the new location. If that fails, we'll try to write to a different location, and if write to a different location fails, the disk group is marked as failed, and will be attempted. The disk will mark as failed, and will be attempted to take to go offline. An interesting scenario is could happen because you never read secondary extents until you actually need to read them when primary is corrupted. If the secondary extent gets corrupted, you can't really notice it until you actually need it, and then it's too late, right? So there's sort of scenario of silent corruptions of the secondary extent. I've never really seen it in production, so I haven't really experienced it, but it is possible. It is possible. So there's a ASM CMD remap command, but what it's used for alongside with the disk scrubbing. Many storage sort of vendors and the arrays have a disk scrubbing or controls for disk scrubbing features. When the disks are idle, it will actually make the disk read the data blocks or the disk locations to make sure they can be read successfully. And if they're read successfully, normally they would send the message by the SCSI bus, and you would see it from the syslog from the server. And if you monitor for that, you would use remap command. So what remap command does is you can tell it which file and which offset you want to read, or actually which disk and which offset you want to read. And if the read is not successful, then it will actually remap that extent. So that's a way to fix that. There is an AMDU utility, which is a little known, but we can analyze from CERN with information on it, and that can be used to actually scan primary and secondary extent, and in fact compare them, match them one-to-one, to see if there's any difference between them. So if there's any concern, then you may have a counter-up, you can use this one. I'm going to skip to this. Disk failure. So as I mentioned a couple slides before, the disk will be taken offline. So when the disk is taken offline, the disk taken offline normally only on the write error. So the read itself doesn't really, the failure of the read doesn't really cause the disk to go offline, because there will be an attempt to fix it. And if it's an attempt to fix it, which will basically makes it right in the end, if that attempt fails, then the disk will be taken offline. There's one exception. If you're reading the disk header and you can't read the disk header, the disk will also be taken offline. There's a few optimizations, I think there's much more than I know about, but a few optimizations done in ASM when it encounters failures of, when it encounters disks going offline. If you have a larger failure group and the whole failure group goes offline, instead of offlining that disk when ASM detects it, when this is going So that's kind of quick walk through the ISM failure scenarios, how ISM handles different failures. And what I wanted to go into next, how much time we have? Started a little late, I only have minutes. Okay. Everything here, except one thing.
Yeah.
Yes. Gotta be fixed. Okay, I want to go a little bit back to stats. How many remember statistics from school or college? No? Good, more than usual. Really good. You can correct me in some things, I'm sure, because I don't remember it very well. So, everybody heard of MTBF, knows sort of what it is. For us, we use it more like mean time to failure, but they're very close, so for our purpose, we don't really need to get into the distinctions of those. So what MTBF is basically an indication of failure rate, indication of failure probability for a disk within its useful lifetime. And if MTBF is 16, let's say 1.6 million hours, which is like 182 years, what it actually means is that it's not likely that this is going to work for that long, right? This will probably be working well within only like 3 years, whatever vendor quotes are the useful life of this device, or this in this case. And during this useful time life of the device, the failure rate will be regulated by this MTBF, and that's kind of the formula how you can calculate it. Let's say analyze failure rate based on the MTBF value that vendor quotes. So the lambda, the formula is basically they're assuming, and all the vendors assume that the failures are distributed exponentially. Lambda would be the failure rate for the interval t. And the MTBF that you put in the formula. So there is a concept known as the bathtub failure rate and curve, and it has sort of a form of a bathtub, that's why it's called like that. So what happens is there's two kind of interesting phenomena. Obviously, when the disk is kind of finishing its useful life, the failure rate grows compared to what the normal failure rate is during the useful lifetime of this disk. But there's also concept of the infant mortality and fake infant morality there, you can read, but that's obviously wrong. And I always leave it like that and I never correct it because it's kind of interesting. So the concept of infant mortality, and what it says is that usually when you just put device in service, the failure rate is usually in the first months, weeks, depends on the device, are higher. And it's definitely true for disks. And manufacturers try to kind of avoid it by running disks sort of in a higher temperature in difficult environments for some time, trying to kind of accelerate that. But they obviously couldn't afford to run them for 3 months, let's say. So it actually doesn't really work all the time. So we still see that even in the enterprise disks. So I looked up some of the results on the internet. Google had an awesome study. So one of them kind of shows that indeed in the first sort of 3 months, you definitely can see an elevated failure rate. So for the high sort of used disks, they see basically average analyzed failure rate 10% for the disk that they use in their data centers, which is, far beyond like orders of magnitude more than vendors would quote in the MTBF. And it'll value that they get during their service of the disks are higher than normal MTBF that manufacturers would quote. So if you take 10% analyzed failure rate for the year, then you can calculate it per hour. The chance of this a spare or would you reuse a spare, and you will start copying the data from the data that is provided to the spare. And it will normally take quite a long time to do that. So, and if you say, and during that time, while you're recovering from this failure, when you're restoring the mirroring, this window, let's call it window of vulnerability. And I use 5 hours here for RAID, for the RAID mirroring. It's never 5 hours. Recovery usually takes much longer, right? So if you take 5 minutes, 5-hour window of vulnerability, and if you use Google's analyzed failure rate of 10% for the first 3 months, then the chance that you're going to lose second disk in the next 5 hours is only 0.05%, which is pretty low. So even with the higher failure rate that Google quote experimentally. But think about a very large ISM disk group. Like think about Exadata with 168 sort of disks, with 168 disks. So if mirror extents would be placed completely randomly to all the disks in the disk group, which is 167 disks, actually 156, is failure group defined. Oracle introduced special concept. So if that was the case, so if extents would be mirrored completely to random disk in random disk in the whole big disk group, in a 5-hour window of vulnerability with Google's 10% failure rate, the chance of data loss to Exadata would be 0.7%, which is very high. Nobody would like that stuff. So it actually doesn't work like that. The way it works is that ISM has a concept of partnering, disk partners. And what it means is that for each disk, it will define number of partners, and it will mirror the secondary extent not to any of the disks within this partner list, not to 168 or 56 disks in this group, but only to the number of partners it has. And by default, I think all 11 versions I've seen, it's 8, and it's regulated by some underscore parameter. So that fixes the problem that we have. So if you calculate sort of probability of data loss after first disk failure, again using Google's 10%, then probability will be 0.04%, which is reasonably acceptable, right? If you take the manufacturer's MTBS sort of 1.6 million hours, which is I think what's on the disks that are in Exadata, for example, then analyzed failure rate would be 12%, and the data loss chance in 5 hours window of vulnerability is only 0.002%, right? And again, they kind of assume that this failure is also on process. What I want to do now is I want to do a demo, and maybe at the end return to it. I usually do it another way around, but I just want to do something different today. So let's try that and see how that works. So I'm going to explain what I have here. I like the environment that I set up with ASM, and I explained how I set it up, because it let me manipulate, let me create failure scenarios for the ASM disks and see how the system would behave. So what I have is I have a virtual machine, and I have an NFS server. I use Mac, so it's Unix. I have an NFS server on it. So, and I create 42 mount points. I exported 42 mount points. If I look in my, and I usually don't go through that very in detail, but I think you may find it useful. So I basically list 42 mount points in my exports file on my NFS host. If you're on Windows, you might have another VM on Linux with NFS daemon on it, with NFS server on it to do the same. Then on the ASM, on the Oracle server, what I do is I mount 42 mount points. Here they are. And I use exactly the same mount options that I would use for data files, pick it up in documentation or recording note. So there's exactly 42 of those here. 42 of those here. And I use a hard option here, and I was arguing yesterday on reception with some it doesn't fail. I was arguing with them, they didn't do it with me. So now that it's recorded on video, I could actually demonstrate it, and it works. And I think the reason it works actually doesn't hang, it generates an IO error from NFS, and instead of just hanging on it. So that's actually the reason it's working. So I guess it depends how you introduce failures. So what I do next is I create a bunch of data files in those mount points. In fact, one data file per mount point. So those are my mount points. /ISM/D and then the number. So main directories, I go to one of them. Each of them has a file disk 100 megabytes of zeros, which I create. What I do next is I can create ISM disk group out of those 42 disks, which are files, but for I would be ISM disks, right? So let me try to do that. And before I do that, let me set up my Windows. I would normally set it up sooner, but I spent an hour fixing my cluster today because it didn't work. But now it does. Works, so it will be okay. Help. Yeah. There we go. Okay, so what am I doing? I'm going to pay ISM alert flow so we can see what's going on behind the scene. My second node of the cluster, but I screwed up the installation. I run the root stage in the wrong order. So my second node becomes the first node in terms of the number, and everything is now backwards. So just to make it fun. I only use one node here in this step, but I could use two and do some fancy things, which we theoretically could do. Okay. And this is the place. This is my so this is my NFS server where I'm going to break disks in a way. So this is my SAM. You think of it as my storage. So, and then it will report in other clock, all the digits are okay, but this number 15 is offline. No, it's not 13, but 15. But that's because it's just randomly numbering them, shuffling them every time you create them. I don't know why, but that's the way it is. That's the way it is. So, think what happened. The disk 15 or 13, depending how you count, has 8 partners right now. And if the next disk that we call ends up to be one of those 8 partners, we will not be able to recover just like that. So right now, disk is offline. We can do L as DSK minus P. So you could see that one disk is offline. There's no path because we couldn't access it anymore. But that's disk number 15. In other block, it will also keep sending the warning messages that disk blah 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 will be dropped in that amount of time. So this is the feature that was introduced in 11.1, I think. In the past, with 10G, if you lose a disk, if disk fails like that, Oracle will immediately start rebalancing, trying to take the disk out of the disk row. Which means if you have a temporary failure of your storage array and the whole failure fails, you end up rebalancing terabytes of data on it. You have a lot of data. So with 11.2, what it does, it will actually track which extents were changed during that time when disk is offline. And then what we could do within this time, and we could change it, we can put the disk back online and recover. And recover much faster because it will only need to resync the extent before change. So not like a terabyte or multiple terabytes if it's available. But we're not going to do that just now. What we're going to do next is we're going to pull another disk and see if we're lucky enough not to keep those 8 disks. And they're pretty random, as you can see, so if you put 14, it will probably be not even, but who knows. Number? 17. It's interesting. It's a favorite number of my son. I knew it should be. 17. Oh. Right. And I wait just a second before I do that, but I think it may be refreshing every 2 seconds. And let's see. Unfortunately, Fritz, you were unlucky. So you hit exactly that. But if you didn't hit that disk, then we will survive. But then what happens next, that disk would have another set of partners. Some of them would be overlapping, but basically on the next failure, you're much more likely to encounter the failures. So I guess that's as fast as it gets. So if you're the most unlucky, so no gambling today for you. But what I'm going to do, imagine it's my temporary failure. I fix the problem I have, my storage controller or something. So I put those disks back into the list of the exports on my NFS server. I don't really need to do anything on my NFS client. The mounts will just automatically work, which is cool. So we look at the disk loading up here. What I can do now is I can online my disk group test right now. ASM will go through all the partners of this disk and see if they all align. So what happened is that the disk that failed, number 17, ASM has this partner status table and it knows certain partners are offline, right? So if you would break 2 disks at the same time and one of them would fail first, it would check the partners through to make sure they're still there before taking the disk offline. So since the partner of this disk was offline, and it's a normal redundancy, not triple, if we just put this disk offline, the data mirrored between those 2 disks would be not available, so we're basically risking the data loss to continue like then I can simply mount this back. Running out of other parts. Okay. And if I mount this group test, and I look at the disk in it, we could see that it actually had only one disk offline. That's because we could not take the second disk offline, so when I mounted it, it came back in the same state. What I could do now, because I fixed the problem, is I could align all the disks to the disk group test, and everything is okay. Everything is okay. Then we will see that all the 40 disks are in service. So what I want to do next is I want to actually do the same thing, but for the high redundancy, and see how long we're going to survive pulling the disk out. Before I do that, I could show you, obviously, you know how to check underscore parameters, but we could check what's our partner target for the ASM disk. If you have less than 8 or 9, cheers. So, I sound much better. Revival. Yeah, we can restart. So, what we could do is we could query some cryptic X dollar, views, of course. These are obviously views which give you all kind of information, and the views which you can read for their to access partners out of table 2. And that's view, of course, called X dollar KFD partner, which is very unusual. Should have been called something else, but not partner. I guess they must have changed the orders. So, and let's see who are the partners for this number 15, which failed, right? 15. So we could see that if we take any of the disks, D2, D24, 17, and etc., it would fail very quickly, right? So if you're curious to see what are your partners, you can always do it. Okay, so what I'm going to do is I'm going to drop the disk group, and I'm going to create it in the high redundancy while it's creating it. potential permutation of partnering depending how lucky we are. Maybe we already offline 2 partners right now. So if we offline any of the partners of those 2 disks, then we would we'd be in trouble. So what I need is another number.
28.
28 at first. Phrase is not allowed to say anything now. 37. Okay, I wrote this number 7. How are we doing? 7 is a lucky number. So we have 4 disks offline. Obviously, I can do a DST minus P and ASM CMD. I could see 4 disks offline. So we're doing well. We're still surviving. You need to be more and more lucky at this point to still survive, but we'll have what you like. I wonder. I wonder. Okay, I gotta check. Hold on. No, not there. That's strange. All right, so 5 disks.
6.
6. I heard something else. Somebody else was spelled, but I heard 6 more. Couldn't record correctly. Nice. Right. This number 6. Oh. Oh, good thing happened. I was waiting for it. So, I didn't run this outer disk group check command, but I still get a failure here. And we still got lucky, by the way, but that's a different story. So, there is several disks allocated in the disk group which contain partner status table, which basically in the header contain information which disk are partnered with which. And what ASM does is that every second or few seconds it actually reads, probes this partner status table, and I think writes to it. Does it write to it? Anybody know? I think it writes to it. Actually. Or at least reads. So, if that disk is not able to perform that operation, it will attempt to mark it offline and nominate another disk to be the disk containing the partner status table. And that's what happened in this case. I didn't need to do alter disk group check command. But and I could do it if you like me to. you can see, triple redundancy is not just a paranoia. It's actually, it can be useful. So when you think about customers who run the group in triple redundancy, think, oh, it's redundancy, ODA triple redundancy. It's actually not that difficult to, lose the data or lose the disk group with the dual redundancy. What I had on the slides, which we obviously don't have time now to go through, is that I had referred some of the work I picked up off the internet from a couple of professors, which I kind of like how they propose to analyze the batch correlated disk failures when multiple disks fail within a short period of time, right? And what they said is if disk files normally within certain probability lambda, then a global defect will manifest itself. Then after that, within a certain time, the probability of disk failure will be lambda double prime, and it will be much, much higher, like once a week, once a month. So it means if you have very high, very elevated potential probability of data loss. And I ran through some formulas. I'll let you go through that yourself if you'd like to. I think we're going to put slides somewhere. Yeah, we're going to have it somewhere. And I also included the SQL statements I use. Before I let you go, because I obviously you all want to go, I'll ask you the question. Remember I mentioned about grade 1 and how probability of data loss in grade 1 was really, really small, was really, really good. And when we looked at, say, 8 partners, and the probability of data loss was much higher, what do you think better? Where do you think probability of survival is better, with grade 1 or with grade 5, which is the same formula, or with the ISM? Do you think grade 1 will fail less likely? You think so? I use window of vulnerability 5 hours in both cases, which is probably not true, because the way rebalancing works in Exadata is there's the mirrors on multiple disks. They will be mirrored to multiple other disks, which will be much faster than just mirror from one disk to another. So the window of vulnerability is much smaller in Exadata, and if you don't touch anything by default, normally it actually will be about 5 hours or something like that. But with RAID 1, it's probably going to be maybe 24 hours or something, depending on the disk size and how quick you're doing it. And if you put it in the formula, it's actually not obvious, depending on the window of vulnerability, it's not obvious which one actually is more likely to lose data, ASM or the RAID mirroring. And with this, thank you very much, and let me go. And are we doing any other sessions, like small talks? Yeah. We're doing small talks, so don't leave anywhere. Are we doing lunch here? No lunch for you. Don't go anywhere. But you have beer, right? No. Boy. I guess everybody can. Is it downstairs? Where's the drink served? I assume it's there. People throw them. They must be here. Thank you.